thank you to Lockheed Martin for sponsoring this series. We couldn't do this without them. So thank you again. So Professor Guo is a professor at Stevens University. She joined the department in 2005. She obtained her PhD in electrical and information engineering from the University of Sydney in Australia in 1999. She was a postdoctoral research fellow at Oak Ridge National Laboratory, and then a visiting assistant professor at the University of Central Florida before starting at Stevens. Her main research lies in autonomous mobile robotics, distributed sensor networks, and nonlinear control systems. So today she's going to be talking about socially assistive mobile robotics. So I will let her start whenever you are ready. Thank you so much.
Thank you, Mumu. Thank you for the invitation. I'm glad to talk about socially assisted mobile robots today. First, I will talk about the motivation. I will introduce some applications of socially assisted robots, and then some fundamental research challenges. And then I'll briefly review some of the current research activities of my lab. I direct the Robotics and Automation Lab at Stevens Institute of Technology. Then I will focus on one particular application of socially assisted robots, that is robot-assisted pedestrian regulation. I'll talk about the learning human-robot interaction in this application. So the use of socially assisted robots is on the rise. These are the example real-world robots that share the environment with humans and interact with humans one way or another. We've seen robot guides, we've seen autonomous robots in airports, in museums, in supermarkets. They can assist in providing directions. They can also assist humans, for example, to help carrying packages. The second picture on the top is actually my friend took later last year in a local supermarket in New Jersey. They deployed a robot to monitor the flow situations. And it was reported last year that California police use robot police to fight crime and keep an eye on the street. Robot researchers also developed robots that help with kids on motor skill training, and robots working with the elderly for rehabilitation or other tasks. So we call this social robots. Mainly, most of them share the same workspace with humans, and also they interact with humans. There are many fundamental research challenges for socially assisted robots. One of it is navigation in human-centered environments. Robot may freeze in place if it's too crowded, using the traditional motion planning method. The robot may treat the humans as moving obstacles. And also, when we share the same space with robots, you don't want the robot always cut in front of you or navigate at the wrong side of the road, so they are against the flow, right? So we need the social compliance of the robot. Also, there are issues like we may want the robot to predict humans' intention and collaborate with humans in various tasks. There are also data privacy issues and transparency issues. We want the robot's behavior to be explainable. So people, when they share the place and work with the robot, and they can understand what the robot is doing. So human-robot interaction is a broad concept in general. Depends on different applications, they mean different things. And there are many application-specific challenges for HRI. My research lab have started working on the social assistant robots about 10 years ago. Currently, we have 2 active NSF-funded projects. The first one is understanding pedestrian dynamics for robot motion planning in human environments. That's NSF M3X project. We started, and this is the second year. Second project is NSF Smart and Connected Health project that we developed integrated robot and wearable sensor system to support aging in place through enhanced mobility and social connectedness. I will talk a little bit more on these 2 projects in the next 2 slides, but this talk we will focus on NRI project we have just concluded last year on dynamic robot guide. So on the first project, understanding pedestrian dynamics, our goal is to develop robot motion planner. As I mentioned earlier, when robots share the same workspace with humans, it's challenging in terms that if they, previous existing method treat moving obstacles in the traditional collision avoidance way, then in crowded environment, robots may freeze in place, and also robot doesn't know the social compliance. It may cut in front of other people, which is not good. So the idea of this project is that we want the robot to learn how humans navigate using the real world human movement data sets. So on the bottom left, this picture is a visualization in ROS that we use open data sets of real pedestrians trajectory in a Japan business center. What happened is that they're smart in navigating in crowd and environment. They may form different patterns. They may follow the leader unconsciously. So we use these open data sets and want to learn human-like navigation features. We tried different machine learning methods, including inverse reinforcement learning, and recently the GALE-based learning. So this video, I hope you can see that, is robot navigating in this Japanese shopping mall business center environments. And we compare the learned navigation behavior with real people's navigation. And we can see that it can successfully follow the flow and have similar motion like a human. Then our second project is integrated robot and wearable sensor systems. We try to develop this system for the elderly people to support the walking exercise. And we want to develop the autonomous gait analysis that using the robot onboard depth image sensors with the wearable sensor that is the smart Insole sensors. So these are the smart Insole sensors that my collaborator, Professor Damiano in ME, developed at Stevens. In this experimental setup, you can see that the mobile robot with a depth sensor can lead the subject to walk, free ground walking, and because we can see that the This video shows the people follow the robot autonomously keep certain fixed distance with the subject. So combine the Insole sensor sense the gate information with the external depth sensor information captured by the robot. We can do the online data analysis. And the goal is to have a robot-guided personalized walking exercise that can provide real-time feedback to engage the elderly. The engagement can be obtained by through the robot, like give a voice, and can also be actuated by a vibration through the shoes, so that the subjects can be trained to walk faster or slower, and engage them to continue. So this is an ongoing project. All right. So far I talked about the two different applications of the project. Takeaway point so far is that robots can be used different ways. Now let's switch gear to independent project that we concluded last year. That's on robot-assisted pedestrian regulation. I will talk for the rest of half an hour at least on this project. Basically, I will first talk about the motivation and the work we do. So for this project, the motivation is the fast is slower phenomenon during evacuation. What happened is that when people in an emergency, people rush to an exit, then there's traffic jam, they block the exit, combined with escape panic, the crowd disaster may happen that may kill people. So it's one of the most challenging issues facing the human society. So previously, transportation researchers have developed the infrastructure modification to improve the pedestrian flow. For example, as shown in the left picture here, they add a zigzag geometry in the indoor environment, the stadium, to improve the flow. And they also can place the obstacles like columns before exit that can help smooth the flow, so that prevent people rush to the exit. The problem with this solution is that usually modification of infrastructure is expensive. Once it's placed, it's not easy to reconfigure. And also, traditionally, they use numerical simulation to decide where to put this column and the shape, optimal shape and place of the infrastructure modification is done by using simulation. So as robotics, we ask, can robot help? So before I talk about our solution, we reviewed literature in robotics. Actually, back in 2003, our robotics researchers have studied the problem of putting a robot in a crowd flow. The robot can affect the flow, average flow velocity, and can change the pattern of the collective motion. And also in a 2013 paper, they discussed the place robot in a train station where there's emerging pedestrian flows. And they can control the robot to move at optimal frequency so that it interacts with the flows to achieve the best guide, which is have the pedestrian flow more smooth and more fluid. But in all this existing approach, they use a simulation study, and what they did are the open loop feedback control. That is, they study the different flow situations and pre-compute the robot velocity and study the robot effect on the crowd dynamics. Offline and online, they choose control the robot accordingly, which is open loop feedback, feed-forward control. In our project, our goal is try to learn the optimal motion behavior for desired collective motion. For example, if the flow condition changes, can we monitor the real flow information using camera, and then the robot adjusts its speed, motion frequency autonomously. And we want to do it online, achieve all this online. So before we start design our learning controller, we did experimental tests to characterize the HRI, human-robot interaction. These videos shows the experiments we did in a garage on campus. We can see in this is a one-dimensional pedestrian flow, and we place a robot in a perpendicular direction against the flow, so people can see the robot, and they see the robot move in front of them, so they maneuver around the robot. This way, we can reduce the speed of this one-dimensional flow. So we want to measure, it's a bit noise here from the video, but basically we want to measure the influence of a moving robot in a unidirectional pedestrian flow. So we set up a network of connected cameras and analyze the data we collected. These two tables on the top shows the measured influence of a moving robot. That we can clearly see the slowdown effect of a moving robot in the pedestrian flow. When the people, so we measured with people either in walking or running, and we found that the slowdown effect is more significant when people are running, when people walk in a faster speed. So this effect is consistent with simulations in the literature using the social force models for pedestrian dynamics. So with the experimental evidence, now we call this passive, we call this passive HRI. That is, humans see the robot and avoid the robot, and robot adjusting the speed accordingly. Based on this HRI, we formulate a robot-assisted pedestrian regulation problem. That is to find optimal robot motion frequency such that the average pedestrian velocity reach the desired value. So our goal is to have a robot move with the flow and adjust the collective average flow of the people when they go to the exit to at the desired value we start. Subject to robot dynamic. This is a simplified double integrator, a kinematic model of robot, and the control variables is the robot moving frequency. In other words, is the speed of the robot. Here, we constrain the robot path to be on a fixed path, which is a straight line in this first case. The feedback control scheme is shown in this block diagram. So we do not explicitly model the pedestrian dynamics and human-robot interaction. Instead, we use external surveillance camera to measure the current flow condition at the axis side, and then that as input to our learning control method, which outputs the robot motion frequency. Then we deploy the robot here. So this is a feedback control scheme. So this slide shows the detail of the ADP learning. So this is a pedestrian dynamics. We use the social force model just in simulation for validation of the algorithm, but in the algorithm design, we do not use explicit pedestrian dynamics model. So the sensor input, we can measure the real-time pedestrian flow. And as the input, it goes into the ADP. Using the neural network approximation, the ADP has two neural networks, one action network that outputs the control variables. The other is a critic network, which estimate the performance real time. So the reward function in this case is a difference of the current flow and the desired flow. And the ADP basically solves the Barman optimality equations iteratively. So this is overall learning control scheme. I don't, for the interest of time, I don't want to choose the detail of this, but it's in the transaction of system magnetic on this 2017 paper. For the details, we have the theoretical proof of the convergence of this method in the paper. So that is a very simple situation in a unidirectional flow, and the robot slow down the traffic. And you may ask, why do you always want to slow down the traffic, right? Actually, that's the first step we did. Our intention is to solve the evacuation problem, the crowd potential crowd stampede, right? But which happens more often in a merging flow scenario. So in a merging flow scenario, it has a high risk of crowd disaster occurrence. We look at a real world example, which happened in 2006 in the Manamaka. Hundreds of people was killed in that crowd stampede incident when tens of thousands of people merged from two flow direction through the bottleneck area. And researchers have studied this incident in quite detail. For example, this paper, they use simulations and some other empirical studies. And this suggested infrastructure modification to improve the bridge situation, like add a ramp before the merging area. So we look at that example environment and scale it down in this simplified illustration. So there's a main flow A and there's a branch flow. So our intention is to deploy the robot in the branch flow to slow down this branch flow so that amount of flow entered in the bottleneck area is controlled to avoid the potential collision. That's our purpose. Now, before we do that, we look at the fundamental diagram. That is, in this merging area, how would the flow of the pedestrian dynamics behave? So these top figures with the density increase, we can see the average velocity of the flow decrease. And also, we can see the it actually have a have a balance that we can achieve. That is, if we maintain the density to a certain level, that's a maximum capacity of this environment, then we can control the situation. So our goal is to have a robot so that we can control the collective pedestrian dynamics at this level. And previous literature also revealed that these key quantities, called crowd pressure, is very important in measuring the risk of cross stampede. The crowd pressure is defined as a product of the local crowd density and the variance of velocity. So in these simulations of particles, we can clearly see that it happens that the traffic jam, right? When the two flows merge with the density increase, the variance of the speed of the local crowd, it may get stuck. So we will monitor the crowd pressure situation. Hopefully, the robot can help reduce such crowd pressure. So use a similar way, we developed this ADP, Adaptive Dynamic Programming-based learning control that use the outflow measurement, the difference of the output flow measurement with the desired flow, which is a maximum capacity as an input. Then output the motion frequency of the robot. So this is ADP learning control, use a surveillance camera, and output robot motion frequency. In other words, a robot will adjust its speed to control the flow of the branch flow to enter this bottom area. If the camera monitored here is very dense, then the robot will move fast. So intuitively, if you have a robot move very fast, eventually like a bullet coming back and forth, nobody will come through. It will cut the flow, right? But of course, in many cases, you don't want to complete cut the flow. That's why you adjust the velocity of the robot. And this ADP learning control algorithm learn the speed of the control autonomously. That's through the ADP learning control. So the simulation results show that pedestrian outflow can increase, and this video shows that with a properly designed robot moving speed, we can reduce the stacking point, the traffic jam that may happen, and keep the flow smooth. We compared the over ADP control, which is a black curve in this figure, with without the robot case, with the robot moving at a random speed, or robot moving or a robot stayed in the middle, for example. You can have robot stay at a fixed position, and over ADP control achieve the best results. In evacuation, this is critical. If you get the flow smooth, it can save people's life. So we measure the significant outflow declines is avoided, and we got the accumulated outflow improved by about 12%, and robot motion frequency can convert to the desired value. This slide shows the crowd pressure. I mentioned that it is an important index to measure the risk of crowd stampedes. So the left figure, we see without robot, the hotspots are where the crowd pressure builds up. And with the robot on the right figure, we can see the hotspot is being removed, and we potentially avoid the crowd pressure build-up. And we that was a MATLAB simulation results. We also validate in the robot simulator in ROS with Pedestrian. Pedestrian use a slightly different social force model and different parameters to simulate the pedestrian performance. So this video shows the snapshots and some simple examples, and we can see the accumulated outflow improved by 8.3%. And in 2 minutes, the people got evacuated out of this area increased like less than 10%, and the robot motion converged to the optimal frequency. We also tested when the flow condition changes. In other words, initially, if the main flow has less people, then the robot may move very slowly, but when the main flow increase, the robot will adjust its velocity online based on the monitored real pedestrian flow situation. All right, so far we discussed the online learning and control by ADP, and we can see that this method can increase outflow and reduce the risk of crowd disasters. However, a limitation for the ADP is that we need explicit feature input. Okay, so I'll explain it more here. Yeah, so we use camera, surveillance cameras, but it needs to have the explicit velocity or the number of people get through. With the advances of the computer vision and deep learning, we want to see if we can use the raw image of the camera to directly learn from the image of the surveillance camera, which will facilitate the online implementation. So we started to look at the deep neural network based method. We developed the so-called end-to-end scheme utilizing representation learning capability of the deep neural network. I hope I have a few more minutes for the next few slides. So first, we formulate the end-to-end learning control in a finite micro-optimization process, MDP framework. We use image observation as the input. Then in this case, we have the robot move in a free walking trajectory. They can move the action space. For the robot, they can move freely up, down, left, and right. And we want to learn, the neural network want to learn the transition between the observation and action space. So we use instantaneous outflow as a reward. That is, we want the number of people going out of the exit to be maximized or reach the capability of the exit. And we define our robot motion planning problem to find the optimal robot policy which maximize expected reward. Note that this policy here not only includes robot speed, but also the trajectory, the directions they go. So it's more complicated than the ADP, that it's moving in 2D, and it's like path planning problem, right? So we use the deep reinforcement learning method that has a 2-layer CNN convolutional neural network and 3-layer fully connected neural network. Use an image of the camera. It goes through CNN to extract features. Then we design a deep double Q learning to learn the motion actions for the robot. And then have the robot deploy in the crowd and real-time adjust its speed. Of course, as same as all the deep learning method, it has to go through extensive policy training. We deploy the robot in random initial conditions and trained the policy, use accumulated outflow. Then we use like 2,000 apples to train it. The performance and the computational cost are detailed in our paper published in the Transaction in Cybernetics 2019. So after training, the control can be deployed to the online motion planning, and robot can move to the optimal position. For example, in this case, a robot starts here, but based on the monitored flow situations, it moves to here, which is the best position to locate, to regulate the flow. When the robot stay at this position, it can smooth out the flow and help mitigate the traffic jam. So we measure the accumulated outflow increase, and this is caused by the traffic jam, and this red color is avoided using the robot assist regulation. All right, so basically for the learning method, I presented the ADP, adaptive dynamic programming based method, and deep reinforcement learning method. This table gives a high-level comparison between these two learning methods. The advantage of ADP is that it can be trained online, and it's very good at online applications. But for the deep reinforcement learning, it has to go through the offline training. And then after training, it can be deployed online to achieve online control. But the advantage of the deep reinforcement learning is that it directly uses images, but not the extracted features from the images as used in the ADP method. The output of the algorithm for ADP is a motion parameters, and for deep reinforcement learning, that's motion trajectory. In other words, the ADP only output the speed of the robot move on a fixed trajectory, but the deep reinforcement learning, it output the motion trajectory, both path and speed. So the computational cost for ADP is low, but for deep learning, it's high during training. We hope it has potential to, our robot assistant pedestrian regulation method has the potential to solve the real world problem of cross stampede. However, here rather limitations. First, we only did it in simulation validation. We haven't done the real world test to deploy robot in a real large amount of people in crowd situation, considering the complication of deploying such system in real world. And also, we didn't consider the escape panic. Escape panic is a complicated issue. There's no, I should say, accurate model of it. And a lot of cross stampede happened with a combination of the traffic jam and escape panic. So in our study, we didn't consider that due to the challenges to model the escape panic. And also we assume the cooperating behavior of pedestrians, that is, nobody throw a robot away. That's, we assume the collaborating behavior of the pedestrians. So these are the limitations if talking about the potential deployment in real world. Okay, so I think my time is almost up. I'd like to leave like at least 10 minutes for questions and answers. But to briefly summarize, basically our contribution in this project is a new problem formulation for robot-assisted pedestrian regulation. And we customize ADP-based learning control and deep reinforcement learning to these applications. For the ADP-based feedback control, we achieve the robot motion adjusted online by learning the human-robot interaction. For the deep reinforcement learning, we achieve an end-to-end scheme, and it has an advantage of image input. But the disadvantage is extensive offline training. In these applications, some future work include extend the single robot to multi-robot cases. That is, if you have more complicated infrastructure like networks or corridors, then you may want multiple robots to regular flow at different places, and they coordinate their motions. So that's multi-robot cooperations. And then the fairness in optimization criteria. In our current work, we only choose the optimal criterion to optimize the output that we want many people go through. But we didn't consider fairness. For example, if we always block the branch flow, then people feel unfair to always be blocked or be blocked for a certain time frame. So fairness is another issue we can incorporate in the optimization criteria. And also we have in the project I just explored, I just talked about, we didn't explore the social aspects of HRI, which is a very complicated issue. There's a lot of discussions of, in simple words, social aspects is challenging topics in the current challenging real world. Okay, so I think I'm going to stop here, and I want to thank my collaborators, Professor Haibo He at the University of Rhode Island, Professor Damiano at Stevens, Dr. Zhen Ni, and my previous student. And all these projects I presented today are sponsored by UNICEF. Okay, that's from me. Thank you all for sticking around during the Friday afternoon. So I'll be glad to address questions.
Great, thank you so much. We have one question already. If anyone else has questions, feel free to sort of write it in the Q&A box. But how would the robot behave when the flow is very minimal?
Yes, that's a good question. So at the beginning, robot is put at the corner. If it deems that you don't need the regulation, robot may just stay in the corner. In other words, output maybe the speed 0 or very slow, so robot will stay at the corner.
Okay. And then the next question is, could you discuss your work on robots in the home?
That is actually a good application. So there's a lot of need for system robot in home. Either autonomous robot that can follow you, monitor you, or robot with arms that can help you grab something. So the second project I talked about for the healthcare robot, it can be used in the home. The robot can act, the aging in place is to help the elderly people live independently in their home. One particular application we can do is, in case of shortage of real humans to lead the elderly people to do the walking exercise, which is very necessary for elderly people. Walking exercise can give them strength, and it's suggested for daily walking exercise for the elderly people. So in case of shortage of the real people, the robot can take them, right, monitor their gait status, and we're developing some techniques that can give the real-time gait information, that if we measure the so-called dynamic stability, that if there's a risk of falling, we'll send alarm so that they can slow down, they can, it can help the walking exercise. That's just one example. And there's many different examples of using the autonomous robots in home. Sorry.
I'm muted. Yes.
Okay.
Yes. Sorry. Okay. The next question. One of the important fields in HRI is physical interactions between humans and robots. As an expert, can you please tell us about the current status and future projections or directions?
Okay. Physical interactions. Yes. So I guess you're talking about like a robot manipulator. You have the robot arm to help you to lift something. So the challenge is when you put human in the loop, how does the robot understand your intention and can, robot has no problem to do it independently, but our physical interaction, I guess the top challenges are safety first for the humans, then robot can understand humans' intention, can predict the human's next move, so that it's safe and it can actually help. I'm not sure I addressed your questions.
So I'm going to the two previous questions, Jay and Gil. I'm just going to allow you guys to talk if you have any follow-up questions to that. And we're trying out this new webinar feature, so hopefully that works. And if that answered it, then we're all good. So no need.
All right, so I'm unmuted. Yeah,
Gil, I can hear you both actually, Jay and Gil.
so should I ask my question?
Yeah, go ahead, Gil.
Yeah, so I've thought a lot about companion robots in the home, and I'd like to get your opinion or comments on the significant failures of companies that have tried to make robots for the home. So think of Jibo, Kuru, which was from Maple Technology, something like that. There've been 4 or 5 of these companies which have been very, very well funded, some of them, and they've almost all failed. Do you have any idea why?
Mm-hmm. Yeah, I'm not particularly familiar with the robots or the companies you mentioned, but I can see it's a challenging problem. First, the entry is high. Not only the hardware, okay, but also there's a lot of uncertainties in the environment. The complication and uncertainty in the real world environment as real complications, even your algorithm works perfectly in a controlled lab environment, but it may not work in the real world. So I'm saying the difficulties and also timing. For companies. And then now I think the most successful is the Roomba, the cleaning robot. They have a good time. It's a time to have the commercial valuable when they develop that. So without knowing the details of the companies that failed, I would say technically, both in hardware and software, there are challenges like the computer vision, right? It's still a lot of challenges to deploy.
Yeah, I would encourage you to look at that because by and large, the reason that the companies failed is that the robots didn't do anything useful. The reason the Roomba is a success is it actually performs a useful function. But you could argue that it's not a robot, it's just a little machine that runs around randomly.
Mm-hmm.
It's not, it just has no human machine interaction. Every time someone tries to build a robot that does human machine interaction, they fail, and they fail fairly dramatically.
Yeah, that's true. The human robot interaction is more complicated because one thing is you need to understand your collaborators' intention, right? I do this. If you just monitor the motion, you may not get me. People, the eye contact, the multi-mode. We communicate with multiple channels. But not a single movement. So your sensors, you have to have multiple sensors that have different types of data. You need to combine real time. So the robot needs training and it needs large data sets to train.
Okay.
A more subtle question than that, but thanks for your answer. Go ahead.
Thank you. If you can type the company's name or robot name in the chat window, I'll check it later. Thank you for your suggestion.
So my previous question, I'm Jay Shim. My previous question is actually related to Gillian Blankenship's question. So I was actually asking you about the physical interaction between the humans and robots. What I meant was when robots work in home or industry and trying to effectively, efficiently work with humans. So for example, okay, I want a glass of water and the robot fetches this a glass and hand it over to me, and the physical interaction between them is really important. So I agree with you that the prediction of the human intention is important. So my lab is actually working on a project to understand the human interactions, physical interactions, in order to, the hope to use the knowledge to develop a later more natural robots with more natural interactions with humans. So what do you think about the learning and applying the human-human interactions to the robot human-robot interactions in the future?
Yeah, thank you for the comments. Yeah, that's a very good direction to work on. There's you know, a good chunk of problems, issues. Good luck.
Yeah, thank you.
Mumu, you are muted.
I keep forgetting. Are there any other questions from the attendees? If not, that takes us to about time. I wanted to thank you so much, Professor, for spending your Friday teaching us about this. And thank you all for coming.
Thank you, Mumu, for invitation. Have a good weekend, everyone.